Yes, let's move on to our third lecture now. Now we are going to see what is the relationship between maximum likelihood and least squared error hypothesis. We have seen that maximum likelihood HML, right, is R max of whatever is maximum of the hypothesis that belongs to hypothesis space H, probability of D given H. Right, this is the maximum likelihood hypothesis. This derivation we have seen in the first lecture of this module. Okay, so if you want to know in more detail, you can refer to that video. Now let us consider the problem of learning a continuous value target function. Say in classification, the machine learning model is trying to learn how to classify between either yes or no, or between female or male, or between defaulter or not, like that. It is the learner is trying to classify between two categories, or in cases multiple classes are there, it is trying to classify between multiple classes. But there may be also some problems where the learner is trying to learn continuous value target function. Say if a model is trying to predict the sale price of a house, or if the model is trying to predict the stock price of a share in the market. In that cases, it is continuous value target function. We call it as continuous value target function. Means whatever is being predicted is not in the form of categories, but it is in the form of values, numbers. Okay, that is called as continuous value target function. Now, let us consider this problem of learning continuous value target function, a problem faced by many learning approaches such as neural network learning, linear regression, and polynomial curve fitting. In linear regression and neural network learning, we normally model them in order to predict some number. Okay, forecasting the weather in the next coming days, or predicting the speed that has to be maintained on the highway for autonomous driving vehicles. All these are predicting a continuous value target function. Okay, in that cases, how actually this maximum likelihood concept has to be understood, that we are going to see. Now, a straightforward Bayesian analysis will show that under certain assumptions, any learning algorithm that minimizes the squared error between the output hypothesis predictions and the training will output a maximum likelihood hypothesis. What do we mean by this? In classification, we can understand, say, when it has to be classified as a good payer of the loan, that data point, if it is classified as bad payer of the loan, then that is prediction error. There is clear difference. When it has to be predicted as yes, it is predicted as no, or when it has to be predicted as no, it has been predicted as yes. There is difference in the classification we can make out. But when we are trying, when the machine is trying to learn continuous value target functions, in that case, the difference between the actual value and the difference between the actual value and the predicted value, if you square them, because sometimes it may be negative, sometimes it may be positive, but we just are interested in the difference only. Now, whether it is positive or negative, we are not bothered. Say the weather has to be forecasted as 34. Actual value is 34, but it is forecasted as 32 on one day. And on the other day, when it has to be 34, it is predicted as 36. In both the cases, we are just interested in, when 32. When the actual weather is 34, it is predicted as 32, and on the other day when it has to be 34, it is predicted as 36. So whether it is positive or negative, we are just interested in the error it has made. That is the difference. That's all. That is why we are squaring it, so that we are not bothered about the negative or positive sign, but we are just bothered about the difference in the prediction, which gives us the prediction error. Okay. Now, a straightforward Bayesian analysis will show that under certain assumptions that data is noise free, data is deterministic, and if the hypothesis is not consistent with the training examples, then it will be 0, probability will be 0, otherwise probability will be 1. If all these conditions are given, it is possible for an algorithm to find out the maximum a posteriori hypothesis that we have learned in the previous class. Now, under these assumptions, any learning algorithm that minimizes the squared error between the output hypothesis predictions, say this is the prediction, this is the output hypothesis prediction 36, and the training data, in the training data it is given as 34 when it is learning. Let us not take the current day forecast or current day weather measurement. Let us see, in training data it is actually 34, but when it is being trained on, it is predicted as 36. So what is the difference here? 2, and square of that is 4, right? So the squared error is 4 here. Now, our objective should be, or any machine learning model's objective should be, to minimize that squared error between the output hypothesis prediction and the training data will output when it reduces that squared error, that will give us the maximum likelihood hypothesis. I'm repeating again, whenever a learning algorithm makes some prediction and you find the squared error of this prediction, that is the difference between the prediction and the actual training examples output, square it. What is that squared error? If that can be minimized, then you can find maximum likelihood hypothesis. If the prediction error can be reduced, then that is nothing but you're going towards finding out your maximum likelihood hypothesis, okay, which will give you accurate predictions, which reduces the squared error in the predictions. Now consider the following problem setting here. Learner L means any algorithm. It can be any algorithm. Learner L considers an instance space X. Instance space means set of training examples. X1, X1, X2, X3 with attributes A1, A2 and A3 and so on. And a hypothesis space H, which contains number of hypotheses H1, H2, H3, which are consistent with the training examples, but we doesn't know their likelihood. We doesn't know which hypothesis is having more probability. Okay, that is the problem we are going to actually learn. We are going to make the machine learn. Space H consisting of some class of real valued functions. Real valued functions means you are trying to estimate some numerical value, predict some numerical value, right? Consisting of some class of real valued functions defined over X. Means this combination of attributes, 2 bedroom, 1 kitchen, 2 baths, this is the sale price of the house situated in this particular locality. Now 4 bedroom, 3 baths and 2 kitchens with extra car parking, this is the sale price of the house. What we are doing here, we are trying to estimate a real valued function defined over X. What is X here? Set of parameters, number of bedrooms, number of kitchens, number of baths. These are all attributes based on which real valued function is being learned. Okay, so the old sale prices and all these training examples will be given. Learning from that, the model should be able to predict the sale price of a house when the number of bedrooms and number of kitchens is given. Okay, that is the problem. Now, each H in H is a function of the form. How the function is represented? X to map to a real number. Real number means X is set of all the attributes. After learning from those attributes, it has to map to a real valued target function. Means it has to map to a sale price in our example. Okay, that should be the hypothesis. In previous cases in classification task, what is the hypothesis? Learning a concept in order to classify something. Here, learning a concept in order to predict some value. How it is learning the concept? By going through the instances X and mapping that to a target real valued function R, where R represents the set of real numbers. It can be any numerical value. Now the problem faced by the learner, that is the algorithm, what it has to learn? To learn an unknown target function f such that X maps to R drawn from the hypothesis space. Even this is a hypothesis. Any target function should come from the hypothesis space H. Okay. Now each training example is a pair of form. Though there are many mathematical notations, they are straightforward. Do not get confused. Just understand what that notation stands for. It will be easy for you to present in the exams. Each training example is a pair of the form xi, a training example with set of attributes, and di, that is your target. Now how should be the target? How is the target calculated? Di is equal to f of xi, a function f of xi with some error associated with it. Now you have been the machine has been given 1,000 houses data and their sale prices. Now you're asking it to predict the sale price when some new data is given about a house. Can it predict appropriately? The exact figure, can it predict? No. Always there will be some error associated with the prediction. That attributes to this EI attributes to that error. Error associated with the prediction task is represented by EI. Remember, predictions are just approximations. They are not exact estimations. That is, when I say exact, I actually should not say estimation. It is not exact calculation. It is just an estimation of something. Prediction is an estimation of something, approximation of something. Means there is some error associated with it. That is represented by EI. So how is the target DI calculated? It is combination of some function which will predict the value plus some error associated with it because it is an approximation. Now the task of the learner is to output a maximum likelihood hypothesis or equivalently a map hypothesis, assuming all hypotheses are equally probable a priori. A priori means beforehand we doesn't have knowledge about the prior probability of any of these target functions. In that case, let us assign just equal probability to all and see which linear function will have highest probability. Select that as your maximum a posteriori hypothesis. Now let us take a simple example here of a problem which is learning a linear function through our analysis applies, though our analysis applies to learning arbitrary real valued function. Before going to this, I'll give you a small example. Based on that, you can understand this concept very well. Okay, now consider there is a salesperson. 1 second. Consider there is a salesperson who comes to houses to service, say, Eureka Forbes water purifier. Okay, now his data will be taken as number of units serviced. Let us take number of units serviced on x-axis and the time taken to service the units on y-axis. Understand carefully. Now, our task is to find out the performance of the service person with respect to the time taken. Means he serviced 2 units in say 2 hours. Then he serviced 4 units in 6 hours. Let this be 4. Yeah, 6 hours. 2 units in 2 hours, 4 units in 6 hours, and then 6 units he has serviced in 8 hours, like this. We have some data points. We have data like this. Now, the learner has to fit a model to this. The learner has to learn from this data points given, so that when number of units serviced by a person is given, by a service person is given, it should estimate what would be the time taken by him to service those units. Okay, that is the problem to be learned by the machine learning model. For this, we can fit least squares method. You have learned least squares method in the first chapter, you remember? So we'll apply this algorithm, or linear regression simply. Let us apply linear regression problem so that it fits a line according to the data points that has been given as training examples. Now, this line is the predictions made, and these are the actual values. First point, it has made correct prediction. Second point, it has made somewhat wrong prediction. Why? Because there is difference between these two. The actual point is here and the original prediction is here, what is made. So there is a difference, that is EI, what I have told you in the previous slide, EI, that is error in the prediction. Again, here also there is some prediction, that is also error in the prediction. Now, what is the goal or what is the objective of the learner? To reduce this error in the prediction as much as possible to get a best fit of all the data points, not only 3 data points. Let us assume there are 100 data points. Now, a linear line means a linear equation should be fit to the data points so that it reduces the error as much as possible. Its prediction accuracy should be as high as possible. Okay, so in this case, now see in this case, this picture, on the x-axis there is independent variable, means predictor, which we are using to predict something, and on the y-axis the predicted variable, the outcome. Okay, so in we have taken say units, number of units serviced by the service person, and what is the time taken. Now, what is this line? This line is called as the intercept. This line, this point where this line is touching the y-axis, that is called as the intercept. And the slope of the line is called as the quotient. Quotient means at what rate x is influencing y. What is the role of x in determining y? Whether it is 2 times or 3 times or 3.5 times or 4.66 times, it depends on the data. How that quotient is being learned by the algorithm, by the machine. Okay, say I get like this, y equal to 4.2x plus some error, say 0.5. Now, if a value is given for x, is it easy to calculate y? Correct, no? So what is this 4.2 here? The impact of this x, the rate at which x influences y. That is called as this quotient, 4.2. This equation will give us this line. This line will give us this equation, y equal to 4.3x plus some error associated with it. This equation is represented by this solid line. Okay, that is the ideal target function that we are trying to learn, which is the best fit to the data points given, which minimizes the error in the prediction. Okay, so this solid line, or here according to this figure, this solid line is taken as f, that is the target value that is learned. But because of this equation, there are some prediction errors. Did you notice? On the line is what is predicted and the actual value is given here. What is the difference between them? That is the prediction error. Here, what lies on this line and what is the actual point? The difference between that is called as the prediction error E. Now, what is the goal of a learner is to reduce this prediction error as much as possible. So that, say, now consider this dotted line. Rather than this solid line, if this dotted line best fits the data points, then we call this dotted line as the maximum likelihood hypothesis. If F itself best fits the data, which is giving lesser prediction error, then we say F itself is the maximum likelihood hypothesis. But rather than this F, there is another dotted line that is identified to be the best fit to this data points given. In that case, this dotted line is the maximum likelihood hypothesis. We call it as maximum likelihood hypothesis, which better explains the data points behavior than this solid line F. Got it? So you have some 3-4 solutions. Among them, which is the best fit to that data points given, that will be your maximum likelihood hypothesis. Got it? Now, F is the linear target function depicted by the solid line and a set of noisy training examples of this target function. Yes. Now, the dashed line HML with least squares training error, dashed line is the hypothesis, maximum likelihood hypothesis with least squared training error. Means when compared to F, HML, this dotted line is having lesser prediction error. So that will become our maximum likelihood hypothesis. So in a plane, if you have 3-4 lines that are fitting your data properly, among them, whichever line is giving the less prediction error, whichever line is giving the least prediction error, that will be your maximum likelihood hypothesis. So that is what is mentioned here. The dashed line is HML with the least squared training error. That is why that is our maximum likelihood hypothesis, because it is giving least squared training error. That is less prediction error. Now, before showing why a hypothesis that minimizes the sum of squared errors in this setting is also a maximum likelihood hypothesis, let us quickly review some 2 basic concepts. So what is our motive now in this session? Let us find out why a maximum likelihood hypothesis is the hypothesis that minimizes the sum of squared errors. Means that minimizes the prediction error. Why is it maximum likelihood hypothesis? Let us see. But before that, we have to understand 2 basic concepts. Those are probability density and normal distribution. Little complicated concepts. Pay interest, students. Stay focused. Okay, now what is probability density? Say you have categorical data. Then you can say this probability of S is higher, probability of S is lower, or probability of male is higher, probability of female is lower, like that. Now, when it comes to continuous valued variables, how do you assess the probability? That can be understood as a bell curve. Say, in India, the life expectancy of Indians is between 60 and 70. Okay, so the life expectancy can be plotted as 60 years and 70 years. Right? Now, if you take the middle point, it will be 65. Now, do you say that all of the people are having this midpoint as 65? No. Some of them may expire at 60 years of age, some of them at 70 years of age. So, most of the population are falling in this range, average 65. That is why we have taken minimum life expectancy is 60 and maximum life expectancy is 70. And most of the population life expectancy falls within this range, among this range. Okay, this is called as probability density of this function. The density of this moderate value is higher. You can't say they have exactly 65 years of age as the final stage or 62 or 63. There is some probability associated with it. Say this probability is lower. This point the probability is lower. But other places the probability is very high. Okay, so for continuous variables, if you take the probability density can be modeled as an inverted bell curve, right? Because the value is continuing. You can't categorize that this has this probability, this has 0.7 probability, this has 0.3 probability. Perfectly, you can say 65, 65.1, 65.2, 65.3, 65.4. It is a continuous value. And each of it has some probability associated with it. That is why where the maximum density lies for the probability, that is of interest for us. So the probability density is represented by P. Probability mass function for categorical variables, it is represented by capital P, and for continuous variables, the probability density function is represented as small p. So this notation is very important when you are deriving it in the exams. You have to be very clear between this P for categorical variables, capital letter P, and lowercase p is for continuous variables. That is representing probability density function. Okay. Now what is normal distribution? Normal distribution is also represented as a bell curve, but here it is the frequency of the data points, not the probability of the data points. Frequency, again I give the same example. In a class, very less number of students will have very less weight and more weight, but most of the students will have average weight, right? This is called as normal distribution. That is also an inverted bell curve. Now this is characterized by its mean mu. Mu lies here, right? With standard and its standard deviation. Standard deviation may not be more than 1. -1 + 1. Okay, this is called normal distribution. Now, how do you represent probability density function in the mathematical form? Did you observe here? We are using small p instead of capital P. Now, probability density function, probability of x naught can be represented as limit epsilon tending to 0, 1 by epsilon multiplied by probability of x naught lesser than or equal to probability of x lesser than x naught plus some error associated with it. Error should always be tending to 0. Means your objective should be to reduce the error to 0. Prediction error to 0. That is why we have given the limit epsilon tending to 0, 1 by epsilon multiplied by the target and the probability of observing x naught lesser than or equal to x less than or equal to error associated with x naught. So you should have this ideal probability density in this range. That is why we have given the limits as x naught and noise associated with x naught. You should not have the lowest value or highest value with noise associated. You should have the ideal value x in between. Okay, that is the probability associated with x naught. Now let us now show that the least squared error hypothesis is the maximum likelihood hypothesis within our problem setting. We shall use P, the probability density function, to refer to the probability density. Okay. Now instead of capital P, what is our HML? Initially, the maximum probability of the hypothesis P of D given H, posterior probability of D given H. But instead of this P, you are using small p. Remember that, because you are trying to find out the maximum likelihood in a real value target function. That is why you wanted the probability density instead of probability mass function. Okay. Now assume a fixed set of training instances x1 up to xm, and therefore consider the data D. All training examples you are taking x1, x2, x3 and so on, and therefore consider the data D, the entire training instances set D, to be the corresponding sequence of target values. Now let us think, for x1 the target real value is D1. Say the first house's estimated value is D1, second house's estimated value is D2, third house's estimated value D3, and so on up to M examples, M training examples. Here, what would be the target function? It is nothing but f of xi, any function f of xi, the learner learns from the training examples plus error associated with it. Any di, any sale price of the house can be represented as an equation of, say, sale price of the house can be represented as a linear equation of, say, 2.5 times number of bedrooms plus 3 times number of kitchens plus 1.5 times number of baths plus 0.5. Say the error associated with it. Now, if the number of bedrooms is given for a new house, number of kitchens is given, number of bathrooms is given, it can automatically calculate the sale price. Now, what is the weight associated with each of these parameters? What are the quotients associated with each of these parameters? That is important for us. And that quotient should be in such a way that the prediction error with the sale price should be as minimum as possible. It should give the best prediction of the sale price, as near to the real value as possible. Okay, so this entire equation is called as f of xi, is represented as f of xi, and this 0.5, some error associated. You are already committing to the error, this much error may be associated. Beyond that, if more error occurs, then there is lot of prediction error in your sale price that is predicted. But if it is very less error, then you say that your model is predicting very well the sale price of the house. Okay, so this entire thing is your f of xi, the linear equation that is built from the training examples by the machine learning model, that is f of xi, and that is nothing but the quotients associated with each of your parameters plus the error associated. That will be your sale price that is going to be predicted. That is nothing but your di. Now it is clear? Now assuming the training examples are mutually independent given h, we can write probability of d given h as the product of various probability of di given h, because probability of d is actually for entire set of training example, but you want to focus here on each of the training examples predictions. That is why you are taking the probability density function p here. So maximum likelihood HML can be represented as argmax of all the hypotheses belonging to H, product of every training examples probability given the hypothesis holds. Okay, you're taking product, you're not taking sigma. Did you observe? You're not adding up all the values, you're multiplying all the values, because this here it is estimating a real value target function. When it is estimating the real value target function, all the probabilities are important here. That is why all the probabilities of each and every point under the curve in the probability density function are important for us. That is why we are making a product of it. Now, when you multiply all the training examples, estimated values, probability of those estimated values given the hypothesis. Among them, which is the highest value, that will be your maximum likelihood hypothesis. Say there are 5 linear equations. Now for all those 5 linear equations, you calculate this hypothesis probability. Now among them, which is having the highest probability, that will be your best linear equation that is explaining the behavior of your data. That will be the best equation into which you can substitute the new data points, the parameters, and you can get the predicted value. Okay. Now the probability density function of di, any estimated value given h, can be written as a normal distribution with variance sigma square. Variance means to a little more value is predicted or little lesser value is predicted. What is the error in the predictions? That variance can be given as sigma square, and the mu is, that is the mean of the values, is mean of all the values that are calculated by the linear equation. Okay. Now a normal distribution, also called as Gaussian distribution. Do not get confused when we say Gaussian distribution. Gaussian distribution is normal distribution only with inverted bell shape. Is a bell-shaped distribution defined by the probability density function. This formula is given for the Gaussian distribution. You have to remember it. Now from this only you can derive other calculations, but the basic formula you have to remember. How you remembered Bayes' theorem? In the same way, you have to remember the probability density function that attributes to a Gaussian distribution, that explains a Gaussian distribution which is having a bell-shaped curve, is 1 by square root of 2 pi sigma square into e power multiplied by e power minus 1 by 2 x minus mu by sigma square whole square. Okay, this is the formula for Gaussian distribution, probability density function which is having a Gaussian distribution. This is the formula. Okay, you have to remember this. Now I will explain you how the maximum likelihood hypothesis is derived. HML, how do you derive it? Argmax of product of all the probabilities, but instead of this probability di given h, for that you are substituting this Gaussian distribution formula. Instead of probability of di given h, you are substituting this Gaussian distribution formula, because we know that this follows a Gaussian distribution. Probability density function of di given h follows a normal distribution or a Gaussian distribution. That is why instead of p of di given h, we can substitute the value of Gaussian distribution directly. That is why we have given 1 by square root of 2 pi sigma square multiplied by e power minus 1 by 2 sigma square di minus mu whole square. Why this is transformed into this? Instead of x, we are considering each training example di. So x is substituted by di minus mean is kept as it is whole square. Now because sigma is a constant, variation is constant across all the samples, bring that out by taking the square as it is, sigma square, that you are bringing it out. So it becomes minus 1 by 2 sigma square in multiplied by, you have instead of x, you have di, that is the training example. Instead of x, you are considering x is training example, and instead of x, you are considering training example instance, that is di minus mu whole square. Okay, now in the next step, instead of mean, you are applying h of xi. Can you tell me why? Because mean of the probabilities is nothing but all the probabilities in the hypothesis space, right? Say if there are n probabilities, then you have mean of the probabilities as 1 by n, because all the probabilities in the hypothesis space They share probability 1. We have the mean probability as 1 by n. Now that 1 by n is nothing but h of xi, where xi, x1, x2, x3, x4 all share equal probability. That is why instead of mu, that is mean of the probabilities, you are just indicating it as h of xi. Okay, mu is substituted by h of xi. Now, rather than maximizing the above complicated expression, we shall choose to maximize its logarithm. So whenever you are maximizing, say if you want to maximize 1000, find maximum value among some 1000 values. Instead of that, if you apply log, it will be easy for you to conquer, because log of 1000 will be actually 3 point something. You know that, right? When you're calculating the logarithm, say you have 10,000. The logarithm of 10,000 is nothing but 4 point something. Logarithm of 1 lakh is 5 point something. So what you're doing here, by applying the log, you are bringing large values to a manageable range. Okay, so for this, let us apply log. For this complex calculation, if we apply log, let us see if we can bring down the terms in the equation. Now when we applied log here, this argmax, observe this line, this equation, argmax h belongs to h. Instead of pi, now we are applying sigma, because we are trying to add up the values. This exponential terms will be added up. When there is a product, you try to add the values instead of, when you apply a logarithm to product of the values, you try to sum them up. Okay, so it has become sigma here. Sigma I equal to 1 to m. Applying the log, this and ln is, you are applying the log 1 by, you take this term as it is because it is a constant. Logarithm doesn't affect that. Minus, now when you apply logarithm to this exponential term, it will become minus 1 by 2 sigma square. Again, there is no change in the constant. And this entire term, that's an exponential term, will come to the front of this logarithm. That is why it is taken as a linear term now, not as an exponential term. When logarithm is applied to e power minus x, it becomes minus x, right, in the linear equation. So this entire term has come to this linear term now. That is logarithm 1 by, log of 1 by square root of 2 pi sigma square minus this entire exponential term has been written directly here. 1 by 2 sigma square into di minus h of xi whole square. Now, the first term in this expression is a constant independent of h. Right? This first term doesn't have any value of hypothesis. If a constant is independent of hypothesis, it doesn't have any effect. So that can be eliminated and can therefore be discarded, yielding. Now in this term, this entire thing will be eliminated. So you get sigma I equal to m. Only this term is left out, minus 1 by 2 sigma square di minus h xi whole square. Okay. Now, maximizing this negative quantity is equivalent to minimizing corresponding positive quantity. Correct? Whenever you are maximizing some negative quantity, it is equivalent to minimizing the positive corresponding positive quantity. Opposite of that, vice versa of that, right? So you are using, instead of argmax, just to remove this negative value, we are using argmin. Understand this line carefully. Maximizing this negative quantity, what we have here, is equivalent to minimizing the corresponding positive quantity. So this, we are writing it as, instead of argmax, we are writing it as argminimum now, so that minus can be eliminated. And you can write the equation as it is. Now finally, we can again discard constants that are independent of x. What other constants we have? This term is a constant. It doesn't have, it is not affected by the hypothesis. So remove it. When you remove that, final value you have as di minus h of xi whole square. Means your training example output and your predicted output. What is that difference? Prediction error. You're squaring them, adding them, and trying to minimize that value so that you will get the maximum likelihood hypothesis. So the objective of any learning algorithm is to minimize the prediction error so that that equation, that best fit equation is the maximum likelihood hypothesis that we have proven here. What is our first starting step here? We started with the Gaussian distribution, assuming that probability density function will have a Gaussian distribution. We substituted the formula of Gaussian distribution, and finally we have proven that the maximum likelihood hypothesis is nothing but the hypothesis which minimizes the prediction error between the actual value and the predicted value. Whatever is the error, that is what is the hypothesis that minimizes this prediction error, that is your maximum likelihood hypothesis. That is what we tried to prove. This shows that the maximum likelihood hypothesis HML is the one that minimizes the sum of squared errors. That is this term. It is minimizing that term between the observed training example, training value di, and the hypothesis prediction hi. We are able to prove that. That is the relationship between maximum likelihood hypothesis and minimizing the least squared error hypothesis. Okay. Now, what are the limitations or assumptions we made in this? The analysis considers noise only in the target value of the training example and does not consider noise in the attributes describing the instances themselves. Say, I'm calculating I'm measuring the students' weight and height in a class. Now, height I can measure accurately, but weight may be having some error, minor error associated with it. In that case, height I can take it as my independent variable, and weight I can take as predicted variable. Weight I can take it as independent variable, and height I can take it as dependent variable, because dependent variable always has some associated error. Dependent variable means predicted variable. Prediction always has some error associated with it. So whenever you are having variables at hand and you wanted to make one variable as predicted variable, see that all the independent variables are error free, and there may be some error associated with predicted variables, not a problem. Okay, so what is the assumption we made here? The analysis considers noise only in the target value, predicted value of the training example, and does not consider noise in the attributes describing the instances themselves. These are the instances: weight, say marks. All these are accurate measurements. We can measure accurately. But height, there may be some error associated with it. So in that case, if you have set of attributes, take all the attributes that are error free as independent values, and if there is some error associated with some variable, take that as predicted value or target value. Okay, that assumption can be made in this context. In the next class, we'll see what is maximum likelihood hypothesis for predicting probabilities. Let us skip the quiz for now. Okay, any doubt in this, students? Did you understand clearly the concept? Lot of mathematics is involved, but still, if you can go through 2 to 3 times the same class. Actually, taking machine learning online class is better. Why? Because the videos will be recorded, and if you have a doubt, you can go through the video once again and go through the explanation. In classroom, if we explain, you can't again get back that explanation, right? So all these mathematical derivations, if you go through the videos 2 to 3 times, it will be very clear for you. Okay? So after the class, please go through the videos once again and also the textbook so that you can strengthen upon the concepts. Okay, we'll meet in the next class.